Okay. Think we're starting? Yeah. Well, hi everyone. I'm Ricardo from Igalia. Most of my work revolves around CTS tests and the Vulkan specification. And today I'll be talking about the new mesh shader extension for Vulkan that was published like a month ago. So I participated in the release process for this extension by writing thousands of tests and reviewing and discussing the specification text for Vulkan, YLSL, and SPIR-V. So mesh shaders are a new way of processing geometry in the graphics pipeline. So essentially, they introduce an alternative way of creating graphics pipelines in Vulkan. But they don't introduce a completely new type of pipeline. The new extension is multi-vendor and heavily based on the NVIDIA-only extension that existed before. But some details are being fine-tuned to make it closer to the DirectX 12 version of mesh shaders and to make it easier to implement for other vendors. So I want to cover basically what you see here, what mesh shaders are, how they compare to the classic pipelines, and how they solve some problems. Then we will take a look at what a mesh shader looks like and how it works, and we'll also talk about drawbacks that mesh shaders have. So mesh shading basically introduces a new type of graphics pipeline with a much smaller number of stages compared to the classic one. One of the new stages is called the mesh shading stage. And these new pipelines try to address some issues and shortcomings with the classic pipelines on modern GPUs. The new pipeline stages have many things in common with compute shaders, as we will see. So this is a simplified version of the classic pipeline. You probably know it very well. And basically, a pipeline can be divided in two parts. The first stages are in charge of generating geometry for the rasterizer. And then the rasterizer does a lot of magic, including primitive clipping, barycentric interpolation, and preparing fragment data for fragment shader invocations, obviously. So it's technically possible to replace the whole pipeline with a compute shader. And I think there's a talk on Thursday about that. But mesh shaders do not touch the rasterizer and everything that comes after it. Mesh shaders try to apply a compute model to replace some of this with a shader that's similar to compute, but the changes are restricted to the first part of the pipeline. So if I have to cut the presentation short for some reason, this is probably one of the slides you should focus on. Like mesh shading employs a shader that's similar to compute to generate some geometry for the rasterizer, and there's no input assembly, no vertex shader, no tessellation, etc. So everything that you did with those stages is now done in the new mesh shading stage, which is a bit more flexible and more powerful. And in reality, the mesh shading extension actually introduces two new stages. There's an optional text shader that runs before the mesh shader, but we are going to forget about it for now to simplify things. So these are the problems that mesh shading tries to solve. Vertex inputs are a bit annoying to implement in drivers, and in some hardware they use specific fixed function units that may be a bottleneck in some cases, at least in theory. The main pain point is that vertex shaders work at the per vertex level, obviously. So you don't generally have control of how geometry is arranged in primitives. So you may run several vertex shader invocations that end up forming a primitive that faces back and is not visible, and there's no easy way to filter those out. So you waste computing power, memory bandwidth, reading data for those vertices, etc. Some implementations do some clever stuff here, trying to avoid these issues. And finally, tessellation and geometry shaders should perhaps be simpler and more powerful, and it should work like compute shaders, so we process vertices in parallel more efficiently and everything. So so far, I've told you that mesh shaders look a bit like compute shaders, and they need to generate geometry for the rasterizer. Because they're so let's take a look. I'm going to give you an example in YLSL to make it easier to read. As you can see, it needs a new extension, which when translated to SPIR-V will be converted into a SPIR-V extension that gives you access to some new opcodes and new functionality, obviously. The first similarity to compute shaders is that mesh shaders are dispatched in 3D groups, workgroups like compute shaders. And each of them has a number of local invocations in 3D controlled by the shader itself. Same deal. There's a limit to the size of each workgroup, but the minimum mandatory limit by the specification, is 128 invocations. And if the hardware does not support workgroups that size, they're going to be emulated. We also have a properties structure in Vulkan, where you can check which is the recommended maximum size for workgroups according to the driver. And inside the body of your shader, you get access to the typical built-ins for compute shaders, like the number of workgroups, workgroup ID, local invocation indices, etc. Obviously, and if subgroups are supported, you may also get you can also use subgroup operations and built-ins and everything in that. But mesh shaders also have to generate geometry somehow. So the type cannot be chosen at runtime. So when writing a shader, you have to decide if your shader will output triangles, lines, or points, and you have to say that in the shader. That's the first thing, different from compute shaders. Then you must also indicate like an upper limit in the number of vertices and primitives that you are going to generate with each workgroup. Generally speaking, this is going to be a smallish number. So in fact, in practice, several implementations will limit you to 256 vertices and primitives at most, which is the minimum required limit according to the specification. And to handle big meshes with this, you will need several workgroups, and each workgroup will handle a piece of the whole mesh, obviously. In each workgroup, the local invocations are supposed to cooperate to generate arrays of vertex and primitive data. So here you can see how. After perhaps some initial processing, you cannot see here, you have to indicate how many actual vertices and primitives the workgroup will emit using this set mesh outputs ext call. And that call goes first before filling any output arrays, and you can reason about it as letting the implementation allocate the appropriate amount of memory for those output arrays or something like that. Mesh shaders output index geometry, like when you use vertex and index buffers together. So you need to write data for each vertex to an output array and primitive indices to another output array. Typically, each invocation handles one position or a chunk of those arrays. And so they cooperate together to fill the whole thing. And in the slide here, you see a couple of those arrays, which are the most typical ones. So you have the built-in mesh vertices ext array, which contains per vertex data, like the vertex position. And this is used with this array go from 0 to the actual number of vertices -1, obviously. And then the primitive triangle indices ext array contains, for each triangle, 3 uint indices into the previous vertices array. That's how it works. The primitive indices array itself is accessed using indices from 0 to the actual number of primitives -1, obviously. And so if there's a second slide that I want you to remember, it's probably this one. What we have here is like an initial template to write any mesh shader. For example, I used like a template like this one when I was writing CTS tests for the extension. There are a few more details we can add, obviously, to the shader. For example, mesh shaders can also generate custom output attributes that will be interpolated and used as input to the fragment shader, just like vertex shaders can. The difference is that in mesh shaders, they form arrays. So if we say nothing, like in the first output here, they are considered per vertex, and they have the same index range as the mesh vertices array. And a nice addition for mesh shaders is that you can use the per primitive ext keyword to indicate that output attributes are per primitive, right? And do not need to be interpolated like the second output you can see there. If you use this, you need to declare them with the same keyword in the fragment shader, so the interfaces match between mesh and fragment. Indices to these arrays have the same range as the built-in primitive indices array, obviously. And of course, if there is no input assembly, we need to read data from somewhere. So typically, you use descriptors like storage buffers containing vertex, maybe index information, whatever, or you can also generate geometry using compute. That also works. Anything works. So just to show you a few more details, these are the built-in arrays used for geometry. There are arrays of indices for triangles, lines, or points, depending on what the shader is supposed to generate. And the mesh vertices EXT array that we saw before can contain a bit more data apart from the position. You have the point size, the clip distances, and cool distances, for example. And then there's a third array that I didn't use before. I'm showing it here for the first time. You can see it's per primitive. It's declared with a keyword. And you can indicate a few things like the primitive ID, the layer, the viewport index, whatever. You can modify and output per primitive data from there. So as I mentioned before, each workgroup can only emit a relatively small number of primitives and vertices. So for big models, you need to dispatch several workgroups, and each of them is in charge of generating and processing what is usually called a meshlet, which are the colored patches that you see here on the bunny. And it's worth mentioning that the subdivision of big meshes into meshlets is typically done when preparing assets for the application. So, meaning there shouldn't be any runtime delay when preparing the meshlets. They are pre-chosen, basically. And then mesh shading workgroups are dispatched with specific commands inside a render pass, and they work very similar to compute dispatches. As you can see here, you specify a 3D size and then launch a number of workgroups for those. So let's talk a bit about task shaders, which are optional in theory, but then Timur will tell you a bit more about them. If they are present, they go before mesh shaders. And the dispatch commands that we just saw do not control the number of mesh shader workgroups. They control the number of task shader workgroups that are dispatched. And then each task shader workgroup will dispatch a number of mesh shader workgroups, and it can decide that at runtime. So it looks like this. Each task shader workgroups also follows the compute model with a number of local invocations that cooperate together. And each workgroup typically processes geometry in some way and amplifies or reduces the amount of work that needs to be done. So that's why it's called the amplification shader in DirectX 12. And once that pre-processing is done, each task workgroup decides at runtime how many mesh workgroups to launch as childs. They form a tree with 2 levels. One interesting detail about this is that compute built-ins in mesh shaders may not be unique when using task shaders. They are only unique per branch. So in this example, we dispatch a couple of task shader workgroups, and each of them decided to dispatch 2 and 3 mesh shader workgroups respectively. So some mesh shaders workgroups will have the same workgroup ID, and even if the second task shader workgroup had launched 2 children instead of 3, even the number of workgroups would be the same for all those. So we probably want them to process different things. So the way to tell them apart from inside the mesh shader is to use a payload, which is a piece of data that is generated in each task workgroup and is passed down to its children as read-only data. Combining the payload with existing built-ins allows you to process different things in each mesh shader workgroup. That's basically how it's done. This is done like this. I just put you in a sample there. So on the left, you have a task shader. It's the first one I show you. You can see it also works like a compute shader, and invocations cooperate to process staff and to generate the payload. And the payload is a variable declared with a task payload shared ext qualifier. So these payloads work like shared memory from the task shader. And that's why they have the shared in the qualifier, obviously. And in the mesh shader, they are read-only. You can declare them the same payload as in the task shader, and you can read data from it. So, advantages of mesh shaders. First of all, you can avoid input assembly bottlenecks if they exist. And you can pre-compute data and discard geometry in advance, saving processing power and memory bandwidth. Geometry and tessellation can be applied freely. More flexible ways, you can do whatever you want because you're in a computer-like shader. And in more flexible ways. And the use of a model similar to compute allows shaders to take advantage of GPU processing power more effectively, in theory. Many games, for example, also use a compute pre-pass to process some data and calculate things that will be needed at draw time. And with mesh shaders, it may be possible to streamline this and integrate this processing into the mesh, or more commonly, the task shader. And you can also abuse mesh shading pipelines as compute pipelines with 2 levels if you need to do so. Disadvantages of mesh shading. For example, mesh shading is problematic for tiling GPUs, as you can imagine, for reasons similar to tessellation geometry shaders, because those reasons. And giving users freedom in this part of the pipeline may allow them to shoot themselves in the foot and end up with suboptimal performance. Timur will tell you some performance tips about that. If not used properly, mesh shaders may be slower than classic pipelines. So the structure of vertex and index buffers sometimes also needs to be declared explicitly in shaders to read from them, like storage buffers. So that increases the coupling between CPU and GPU code, which is not nice. But probably the most important drawback of mesh shading right now is that it's hard, or sometimes even impossible, like we could say, to write a single mesh shader that performs great on all implementations. That's the main disadvantage. So some vendor preferences are exposed as properties by the extension, and you can read those. And you can see that NVIDIA loves smaller workgroups, if possible, and using loops to encode to generate geometry with each invocation. So several vertices and triangles per invocation. That's what NVIDIA likes a lot. And then threads on AMD, they typically can only generate at most 1 vertex and 1 primitive. So they love you to use bigger workgroups and use the local invocation index to access per vertex and per primitive arrays. So they can apply a lot of optimizations and everything. So as you can imagine, this probably results in different mesh shaders for each vendor, even if both are mesh shaders. And that's it. Questions?
If anybody has questions, we can throw that at you and speak to that thing.
Careful.
I'm curious just about if you look at Metal 3, their shader implementation, and how that, what they support, how that compares to the extension.
Sorry, can you repeat?
And the Apple, their Metal 3 support, in Metal 3 they have mesh shader support, which they introduced. I'm just curious how that compares in terms of to the function spec you.
So the question is how, I had to repeat the question for people. Yep. So the question is, how do mesh shaders in Apple Metal differ from this? And it's a bummer because I have no idea. I have never worked on Metal, so there's...
I wonder if, is it viable to implement the classical pipeline on top of the mesh shader pipeline, or will hardware need separate pipelines there?
I don't know. It's I think in theory it's possible because you can emulate basically. Timur wants to say something. Oh yeah, I have to repeat the question. If it's possible to emulate the classic pipeline using mesh shaders, and in theory it is, using some tricks, because you have the vertex input assembly, so you can generate mesh shader code for reading that, and then everything works the same. But you have to use mesh shaders to emulate tessellation and geometry shaders. That's going to be a bit more complex, but yeah, in theory, I think it can be done because it uses the same hardware in practice.
I just want to ask, would it make sense to characterize task shaders as something that basically decides how to dispatch the mesh shaders? Is that what you're saying?
Yeah, and so the question is if task shaders are used to decide how to dispatch the mesh shaders. Yeah, so that's basically what they are used. They are called the amplification shaders. You can decide, for example, Timur will tell you more about that, but you can use it for choosing load levels of low detail, or you can cut things short, like this is not visible, this whole thing is not visible, so I'm not going to launch anything to try to generate geometry for this part of the scene or something like that. They can be, task shaders usually try to pre-process geometry and do some selection and launch the appropriate number of mesh shader workgroups so it works optimally and doesn't waste hardware resources. So it's very important in practice. It's very important to use task shaders to decide how many mesh workgroups you really need and to do some work there.